Before we begin exploring transformer neural networks, it helps to step back and understand why this architecture became so important in modern artificial intelligence. Over the past decade, transformers have become the dominant architecture in AI. They power many of the systems people interact with every day, from language translation tool to conversational AI systems to models that generate text, images, and even video. What makes transformers so powerful is the way they process information. Earlier neural networks often struggled to understand long sequences of information, especially when the meaning of something depended on context that appeared much earlier in the input. Transformers introduced a fundamentally different idea. Instead of processing information step by step, they rely on a mechanism called attention, which allows the model to focus on the most relevant pieces of information across the entire input. This makes it possible for transformer models to understand relationships across large amounts of data simultaneously. As a result, transformers scale extremely well. They can be trained on enormous datasets, and they can support some of the most advanced AI systems ever created. In this module, we will explore how transformer neural networks work conceptually, why attention mechanisms are so powerful, and how this architecture enables modern AI systems across language, vision, and multimodal applications. To understand why transformer neural networks were introduced, we first need to look at the limitations of earlier neural network architectures. Before transformers, many sequence-based problems were handled using recurrent neural networks, or RNNs. These models processed information one step at a time. For example, when analyzing a sentence, the model would read the first word, then the second word, then the third word, continuing sequentially through the entire input. This approach works reasonably well for short sequences. But as sequences become longer, several important problems begin to appear. First, sequential processing makes training slow and computationally expensive because the model cannot process all parts of the input at the same time. Second, recurrent models often struggle with what researchers call long-range dependencies. In many real-world situations, the meaning of a word may depend on something that appeared many steps earlier in the sentence. But as information passes through many steps in a recurrent network, that earlier context can gradually weaken or disappear. As a result, the model may lose important information. Transformer neural networks were introduced to solve these challenges. Instead of processing information sequentially, transformers allow the model to examine relationships across the entire input simultaneously. This shift from sequential processing to attention-based processing is what made transformer architecture so powerful and ultimately enabled the large-scale AI systems we see today. One of the most important ideas behind transformer neural networks is the concept of attention. Attention is the mechanism that allows a model to decide what information matters most when making a prediction. In many types of data, especially language, not every piece of information contributes equally to meaning. Some words, phrases, or elements in the input may be far more important than others. Attention allows the model to focus on the most relevant parts of the input, while giving less importance to information that is less useful. To understand this idea, imagine reading a sentence. When you interpret the meaning of a particular word, you naturally pay attention to other words that influence its meaning. For example, pronouns such as he, she, or they depend on earlier words in the sentence to make sense. Attention mechanisms allow neural networks to perform a similar process. The model evaluates relationships between different parts of the input and assigns different levels of importance to each connection. In other words, the model learns which pieces of information should influence each other. This ability to dynamically prioritize context is what allows transformer models to build a much deeper understanding of complex data. And it is one of the key innovations that made modern, large-scale AI systems possible. Now that we understand the idea of attention, we can explore one of the biggest differences between transformer networks and earlier sequence models. Traditional recurrent neural networks process information step by step. If the model is reading a sentence, it starts with the first word, then moves to the second, then the third, continuing sequentially until the end of the sentence. Each step depends on the result of the previous step. This means the model cannot analyze later parts of the sequence until earlier parts have already been processed. While this approach allows the network to maintain a form of memory, it also creates several limitations. Training becomes slower because the model must move through the sequence in order. And more importantly, long-range relationships can become difficult to capture. Transformers approach this problem in a completely different way. Instead of processing inputs sequentially, transformers analyze all elements of the sequence at the same time. Through attention mechanisms, the model can evaluate how every part of the input relates to every other part. This means the model can immediately detect relationships between words, even if they appear far apart in the sequence. By removing the requirement for sequential processing, transformers dramatically change how efficiently models can learn from complex data. And this architectural shift is what made large-scale AI training much more practical. One of the most important consequences of the transformer architecture is the ability to use parallel processing. In earlier neural network models, especially recurrent networks, information had to be processed one step at a time. Because each step depended on the previous one, the model could not move forward until the earlier computation finished. This created a natural bottleneck. Even with powerful hardware, the model was forced to work sequentially. Transformers remove this limitation because attention allows the model to analyze relationships across the entire input simultaneously. Many computations can occur at the same time rather than in sequence. This means the model can fully leverage modern computing hardware, such as GPUs and TPUs, which are specifically designed to perform many operations in parallel. The result is a dramatic improvement in scalability. Models can be trained on much larger datasets. They can also grow to much larger sizes, with billions or even trillions of parameters. This combination of attention mechanisms and parallel computation is one of the main reasons transformers became the dominant architecture in modern artificial intelligence. Without this ability to scale efficiently, many of today's most advanced AI systems simply would not be practical. Now that we understand how transformers process information, we can look at where this architecture is actually used. Today, transformer neural networks power many of the most advanced AI systems across multiple domains. One of the most well-known applications is in natural language processing. Transformer models are used for tasks such as language translation, conversational AI, text summarization, and large-scale text generation. These systems are able to understand context across entire passages of text, which allows them to generate responses that are much more coherent and contextually relevant. But transformers are not limited to language. Researchers have also adapted this architecture for computer vision. Vision transformer models analyze images by learning relationships between different regions of the visual input, allowing them to recognize objects, patterns, and structures within images. More recently, transformers have been used to build multimodal systems. These systems can analyze and combine multiple types of information at the same time, such as text, images, audio, and video. For example, a multimodal AI system might analyze an image, while also interpreting a written description of that image. Because the transformer architecture is flexible and scalable, it has become the foundation for many modern AI systems across industries, and its influence continues to grow as researchers expand its capabilities into new domains. As powerful as transformer-based AI systems have become, they also introduce important risks and ethical challenges that we must carefully consider. One major concern is bias. Transformer models learn patterns from extremely large datasets, and those datasets often reflect the biases that exist in society. As a result, the model may unintentionally reproduce or amplify those biases in its predictions or generated content. Another concern is misinformation, because transformer systems can generate highly realistic text, image, and other forms of media. They can potentially be used to create misleading or false information at large scale. This raises important questions about trust, verification, and responsible use of AI technologies. Privacy is another critical issue. Many transformer models are trained on massive collections of publicly available data. Without careful safeguards, there is a risk that sensitive or private information could appear in training data and influence model outputs. Finally, there is the issue of misuse. Like many powerful technologies, transformer-based AI systems can be used for both beneficial and harmful purposes. They may be used to automate helpful services, improve accessibility, and accelerate innovation, but they could also be misused to generate spam, deepfakes, or other forms of harmful content. For these reasons, the development of transformer systems must be accompanied by responsible governance, transparency, and ethical oversight. Understanding both the capabilities and the risks of these systems is essential for anyone working with modern artificial intelligence.